Okay, welcome back. I want to talk for hopefully just 5 minutes about the Euler Totient function. And this is something I know almost nothing about. So don't ask any questions. What is the Euler Totient function? It says it's the number of integers. So for a given n, for a given positive integer n, it's the number of positive integers up to and including n which are relatively prime to n. Okay, so for example, take some number like 84. Well, what is the prime factorization of 84? That's 2 times 42, which is 7 times 6, which is 2 times 3 times 7. So I guess that's 2 cubed, 2 squared, times 3 times 7. And so what numbers are going to be relatively prime to 84? Well, they will be numbers which have no prime factors or no factors in common with 84. And you have no factors in common with 84 if you are not divisible by 2, not divisible by 3, and not divisible by 7. So we're looking for, so the answer to this, well, I'm not going to tell you the answer right now, but this function applied to, I guess, this phi of 84 would be all the numbers which are relatively prime to 84. So numbers which are prime, you know, like 31 or whatever, but also numbers like 25, which doesn't have a 2, 3, or 7 as a factor. Okay, how can we compute this? Well, you can do it using the inclusion-exclusion principle. And first, I think this is the best way to explain this. First, let's just recall a fact from algebra. So algebra fact, this is something you learned in Pre-Calc C, or in functions, or you forgot. It basically is the Vieta's formula, the sum and product of roots formula. But anyway, or you can just kind of do it. I think this is the best. Well, we'll see. Take the product x minus a, x minus b, x minus c, and when you multiply this all out, what you in fact get is x cubed. This is just a polynomial. It has 3 roots. The 3 roots are a, b, and c. And in fact, when you multiply the polynomial out, what you get is x cubed minus the sum of the roots plus the minus the sum of the roots plus the sum of the pairwise products. So that's AB plus AC plus BC x, and then minus the sum of the triple-wise products, which is ABC. And this is actually already sounds almost like the inclusion-exclusion principle, and you could even maybe give a kind of a combinatorial argument for this piece of algebra. But for the purposes of our proof, let's just take that as a fact of algebra. Okay, so keeping this in mind, and it's true. Let's try to calculate it in general. Oh, maybe first I should just say the theorem. Here's the theorem. The theorem is that to do this, quite incredible, all you have to do is take the number n and you multiply by 1 minus 1 over p1 times 1 minus 1 over p2 times, and you keep on doing this all the way up to 1 minus 1 over PR, where P1, P2, P3 to PR are the prime factors of n. Okay, so this is the general form of this theorem. Says take any number. If you want to know the number of positive integers up to and including that number which are relatively prime to it, then you take the prime factorization of that number, you reciprocate, subtract from 1, multiply together, and n. Okay, and we can talk for a minute about why that's kind of obvious. First, let's do the proof. And by do the proof, I mean let's just do it for the case of 84. I'm going to squeeze this into this space right here. So, okay, how can we do this with 84? Well, what are we actually trying to do? What is the definition of this function? It's defined sort of semantically as the answer to a counting problem. It's the number of integers which are relatively prime to 84. I'll just write that down. This is the number of integers in the set 1, 2, 3, all the way up to 84. Which are relatively prime to 84. And what does it mean to be relatively prime to 84? As we already said, it means that you have no factors in common with 84, which means that your prime factorization does not have a 2, 3, or 7 in it. So basically what we're counting here is the number of integers from this set which are not divisible by 2, 3, or 7. And the problem is, okay, so let's do this. Note that there is this not in our present here, and so it could be quite difficult to count the number of numbers which are not divisible by 2, 3, or 7. So instead, let's count the numbers of numbers which are divisible by 2, 3, or 7. Okay, and so what I'm going to do is I'm going to take 84, which is the set of all the numbers in this set 1 to 84, of course, and I will subtract all the numbers which are divisible by 2, 3, or 7. And if I subtract all the numbers which are divisible by 2, 3, or 7, then I'll get the numbers that are not divisible by 2, 3, or 7. Okay, well, how many numbers are divisible by 2, 3, or 7? Well, how many numbers are divisible by 2? Because 2 is a factor of 84, then how many numbers are divisible by 2? Well, of course, it's going to be 84 divided by 2. How many numbers are divisible by 3? Well, that's 84 divided by 3. How many numbers are divisible by 7? Well, that's 84 divided by 7. Okay, so if you don't think about this too much, you might think, oh, we have just counted all the numbers which are divisible by 2, 3, or 7. It's just the division. But of course that's wrong, because there are numbers which are divisible by 2 and 3, such as 12. And so we've counted 12 as a number which is a multiple of 2, but we've also counted 12 as a number which is a multiple of 3. And so there's some overcounting going on, and this is exactly what the inclusion-exclusion principle guides us to be careful about. Ultimately what we are doing, I don't feel like writing this down because there's no space, is we're trying to find the size of the set of numbers which are divisible by 2 or 3 or 7, and so to count that set we take everything in this set plus everything in this set plus everything in this set, and there are clearly this number of them, but now we need to subtract by the numbers that we've overcounted. Well, we need to basically subtract out all the multiples of 6 because they are both multiples of 2 and multiples of 3. And how many numbers are multiples of 6? Well, 84 divided by 6. How many numbers? Then we also need to count all the numbers which are multiples of 2 and 7. So 14, for example, and 42 got counted twice here. So I subtract out 84. I'll write this as 2 times 3. I think it's more clear. 2 times 3. And this is 2 times 7. And then we also need to subtract out all the numbers which are multiples of 3 and 7. So that's 84 divided by 3 times 7. But now you see that we have still don't have the right answer, because if there's a number which is a multiple of 2 and 3 and 7, like, well, 42 I guess, and 84 itself, then it got counted once as a multiple of 2, counted once as a multiple of 3, counted once as a multiple of 7, but then it got subtracted as a multiple of 6, it got subtracted as a multiple of 14, and it got subtracted as a multiple of 21. What did I do wrong? 2 to 42, yeah. Yeah, of course. Yep. So I need to add it back in. And this is a casual use of the inclusion-exclusion principle at play here. So this is going to be 84 divided by 2 times 3 times 7. And now, this stuff in brackets should be an accurate accounting of all the numbers which are multiples of 2, 3, or 7. Okay, well, the thing we can do now here, of course, is to factor out an 84. Whew. And then what we have is 1/2 plus 1/3 plus 1/7 minus 1/2 times 1/3 minus 1/2 times 1/7 minus 1/3 times 1/7 and finally plus 1/2 times 1/3 times 1/7. Cha-cha. Okay, and now hopefully you see the connection here. This is, if we group a little bit differently, let me do this, put some parentheses like that, and then so change those to pluses, and then stick some parentheses here. Then we see that in fact this is exactly what we have down there in that final step. It's the sum of the three numbers. Yeah. What happened here exactly? Oh, I just lost my minus. This is 84 minus all of that. So is that now something wrong? No. Oh, I see what happened. When I factor out the 84, sorry, then that should be 1 minus. There we go. So factor the 84 out of everything, so the brackets kind of moved. Sorry about that. So this is 1 minus the sum of these three numbers. Then this should become a plus now. Cha. Yeah. And then that should become a minus, because of course I did factor out the negative. Okay, so what do we see? 1 minus the sum of these three numbers plus their pairwise products minus their triplewise product, of which there's only one. And so this is, by this algebra principle, then this whole thing becomes 84 times 1 minus 1/2 times 1 minus 1/3 times 1 minus 1/7. And in fact, what we get if we just continue doing out this example, so this sort of proves the theorem, so to speak. This is the theorem that we were proving, but instead of proving it in general, because there's no point in doing that, I just did it for a particular example. The argument is exactly the same in general. That's what you get, right? You take the reciprocal of the prime of each of the prime factors, subtract from 1, multiply them all together, including the number. So the theorem is proved. Let's just finish this conversation though. That's of course 1/2, and that's of course 2/3, and that is of course 6/7. Okay, so and then what you get when you multiply all these numbers together is well, you just get 24. Okay, why does this make complete and total sense? I think the place to look is just right here, and in some ways this theorem is extremely intuitively obvious, because what is this thing in blue saying? It's saying, yo, take 84. Well, take half, so I'm looking for all numbers which are not multiples of 2, 3, or 4. 2, 3, or 7. Well, half of the numbers are not multiples of 2. So if I take all the numbers, and I multiply by the half which are not divisible by 2, then I get the numbers which are not divisible by 2. Well, now of those numbers which are not divisible by 2, and now we are sort of using the property of the primes, which is that they're all sort of, well, of those numbers which are not divisible by 2, a third of them are going to be divisible by 3, and 2/3 of them aren't going to be divisible by 3. So if I multiply the product of these two as the numbers which are not divisible by 2, and I multiply that by 2/3, because 2/3 of those are not divisible by 3 either. So then 84 times 1/2 times 2/3 is the numbers which are not divisible by 2 or 3. And of those, 1/7 of them are going to be multiples of 7, but 6/7 of them are going to be not multiples of 7. And so multiplying 6/7 by the numbers that are not divisible by 2 or 3 gives you the numbers which are not divisible by 2 or 3 or 7. And so in some ways, it's just totally obvious that this is a correct analysis. And going to the general case, you just perform that same argument again, right? for each of the prime factors of your number n, this factor represents the proportion of them which are not multiples. 1 over p1 is the proportion of them which are multiples of prime factor p1. So 1 minus 1 over p1 is the fraction of them which are not multiples of p1, and 1 minus 1 over p2 is the fraction of them which are not multiples of p2, etc. And so the product of all of those is the numbers which are not multiples of any of those prime factors. Okay, but the actual proof of this uses the inclusion-exclusion principle in a certain kind of way, plus a piece of algebra. Okay, good, bye.